commercial suite experienced a total power loss. The customer reported a loud pop and erratic thermostat behavior. Upon arrival, the 208/120 volts three-phase main panel showed no voltage, and the main 150 amp three-phase breaker in the meter room was in the on position, but had no voltage on the load side. The breaker could not be switched off and was stuck in an intermediate position. Fortunately, spare meter sockets allowed for breaker swapping. After confirming no shorts in the feed, the panel was re-energized with all breakers off, restoring power. Individual 120 volts breakers were then turned on one by one without issue. The suite contained a furnace with 60 amp fuses, a duct heater with 40 amp fuses, a rooftop unit with 30 amp fuses, and a water heater with a 30 amp breaker. All fuses were initially found to be intact. The water heater was tested and functioned correctly. Each piece of heating, ventilation, and air conditioning equipment was inspected individually. This included checking fuses, testing for shorts in the feeder, and re-energizing with the disconnect off, all of which appeared normal. The furnace and duct heater were turned back on, but the rooftop unit was left off due to observed rust on the compressor. The customer was advised to have the heating, ventilation, and air conditioning system thoroughly inspected, suspecting a potential fault within the equipment or a failure of the main breaker. The question arises, if a piece of equipment faulted severely enough to trip a 150 amp main breaker and render it inoperable, why wouldn't the individual breakers or fuses trip as well? Furthermore, if the main breaker simply failed, why would the customer hear a pop, considering the separation between the suite and the meter room? Let's consider potential causes and what might have been missed during the troubleshooting process. Firstly, it's possible that the initial fault was a high impedance fault. This type of fault doesn't draw enough current to immediately trip a breaker or blow a fuse, but it can still cause damage and potentially lead to a more significant failure. A high impedance fault could explain the pop sound and the eventual failure of the main breaker. Secondly, the main breaker itself could have been faulty. Breakers can fail over time, especially in commercial settings where they are subjected to frequent use and varying loads. A weak breaker might trip at a lower current than its rating, or it might fail to trip at all under certain conditions. The pop sound could have been the sound of the breaker failing internally. Thirdly, the heating, ventilation, and air conditioning equipment, particularly the rooftop unit, could be the source of the problem. The rust on the compressor suggests potential corrosion or internal damage, which could lead to an electrical fault. A failing compressor motor, for instance, could draw excessive current intermittently, eventually causing the main breaker to fail. Fourthly, the age and condition of the electrical system should be considered. Older electrical systems are more prone to failures due to deteriorated wiring, loose connections, and outdated components. A thorough inspection of the entire electrical system, including wiring, connections, and grounding, is recommended. Fifthly, the possibility of a transient voltage surge or spike should not be overlooked. Voltage surges can damage electrical equipment and cause breakers to trip or fail. A surge suppressor installed at the main panel can help protect against voltage surges. Sixthly, the load calculations for the suite should be reviewed to ensure that the electrical system is not overloaded. An overloaded system can cause breakers to trip frequently and eventually lead to component failures. Seventhly, the type of breaker used in the main panel is also important. Some breakers are more sensitive to certain types of faults than others. An electronic trip breaker, for example, may be more sensitive to ground faults than a thermal magnetic breaker. The correct type of breaker should be used for the application. Eighthly, the ambient temperature can affect the performance of breakers. High temperatures can cause breakers to trip at lower currents, while low temperatures can make them less sensitive. The temperature rating of the breaker should be appropriate for the environment. Ninthly, the maintenance history of the electrical system should be reviewed. Regular maintenance, such as tightening connections and inspecting components, can help prevent failures. A lack of maintenance can increase the risk of electrical problems. Tenthly, it is crucial to understand the sequence of events leading to the power outage. The customer's report of a loud pop and erratic thermostat behavior suggests that the problem may have been developing gradually. The thermostat issue could have been a symptom of a voltage fluctuation or a failing component in the heating, ventilation, and air conditioning system. Additionally, it is important to examine the failed main breaker for any signs of damage or overheating. A visual inspection may reveal clues about the cause of the failure. Look for signs of discoloration, melting, or arcing. Consider having the breaker tested by a qualified electrician to determine its condition. Furthermore, it is important to follow up with the customer and the heating, ventilation, and air conditioning contractor to gather more information about the heating, ventilation, and air conditioning system. Ask about the age of the equipment, its maintenance history, and any recent repairs or modifications. This information can help narrow down the possible causes of the power outage. In conclusion, the power outage in the commercial suite was likely caused by a combination of factors, including a potential fault in the heating, ventilation, and air conditioning equipment, a failing main breaker, and possibly other underlying issues with the electrical system. A thorough inspection and testing of all components are necessary to identify the root cause of the problem and prevent future occurrences. Based on the information provided, it's difficult to pinpoint the exact cause of the loud pop. However, several possibilities exist. One is that the pop was related to the failure of the main breaker itself, perhaps an internal component arcing or breaking down. Another possibility is that the pop was caused by a surge or transient voltage event, potentially damaging the breaker or other equipment. In addition to the above considerations, several other factors could have contributed to the power outage. These include loose connections, corroded wiring, and improper grounding. Loose connections can create resistance, leading to heat buildup and eventual failure. Corroded wiring can reduce the ampacity of conductors, causing them to overheat and potentially start a fire. Improper grounding can create a path for stray currents, which can damage equipment and pose a safety hazard. Another possibility is that the customer misidentified the source of the pop. It could have originated from a different piece of equipment in the suite, such as a lighting fixture or an appliance. It is also important to consider the possibility of an external factor, such as a power surge from the utility company. Power surges can occur during storms or other events and can damage electrical equipment. To further investigate the cause of the power outage, it would be helpful to perform a thorough inspection of the electrical system, including the main panel, the branch circuits, and the equipment connected to them. This inspection should include checking for loose connections, corroded wiring, and proper grounding. It would also be helpful to test the main breaker to determine if it is functioning properly. This can be done using a breaker tester, which applies a controlled current to the breaker and measures its response. The customer also indicated that the thermostat acted squirty when they arrived in the morning. Thermostats are low-voltage devices, often 24 volts alternating current. The transformer that powers the thermostat may have been failing, creating a voltage fluctuation that affected its operation. Or there may have been a wiring issue with the thermostat itself. It could be a completely independent incident, or may have been correlated with the incoming power problem. When turning the breakers back on, one by one, you mentioned that all breakers worked when they were turned on, including the water heater. What was the amp draw on that breaker? Was it close to 30 amps? If so, this could have contributed to the problem. As you said that there was rust on the compressor of the rooftop unit, but you didn't mention rust anywhere else. Check for moisture on the conductors and the equipment. Was there condensation in any of the junction boxes, either on the load or line side of the main breaker? Moisture can create a current leak which can cause all sorts of issues. Also, check the torque of the bolts on the breakers and the equipment. Loose connections can be a huge culprit. The type of wire used also matters. Aluminum is a great conductor, but over time it can expand and contract, causing it to loosen. Use a torque screwdriver per the electrical code.